So here is the physical properties of haloalkanes and haloarenes. So the first physical property is they are colorless when pure. So in their pure state they will be colorless. But there is exception, bromides and iodides. If haloalkanes and haloarenes means there will be halogens. Okay, halogens. If the halogen connected are bromine or iodine, if they are bromine or iodine, they will possess color when exposed to light. In pure condition they will be colorless, but bromides and iodides will have a color when exposed to light. Okay, and they have a sweet smell. And now when we look into the melting and boiling points of these haloalkanes and haloarenes, CH3Cl, CH3Br, CH3CH2Cl, CH2ClF, which is called freon gas. Okay, so these all are gaseous at room temperature. Gaseous at room temperature. Now the higher members are liquid or solids. They may be liquid or either solids too. The lower members are gaseous at room temperature. Now they are polar in nature. They are polar in nature because here we have CH3 group and here is a Cl group or a Cl atom. This chlorine is highly electronegative, so it will attract the shared pair of electron towards it, inducing a partial negative charge on this chlorine and a partial positive charge on this methyl group, so that there is a polarity. And due to the greater polarity and they have greater molecular mass, chlorine will have greater molecular mass, and this causes a greater molecular mass to the whole haloalkane or haloarenes. So due to two reasons, great polarity and higher molecular mass, they have stronger intermolecular force of attraction. Okay, as compared to the parent hydrocarbon. Parent hydrocarbon means what? It will be lacking that halogen atom. It will be lacking that halogen atom. Instead of that, it will be having hydrogen. Like CH3Cl is a haloalkane. The parent hydrocarbon of CH3Cl is CH4, because CH3Cl is obtained by replacement of one hydrogen from CH4. Okay, so as compared to CH4, CH3Cl will be having greater or higher molecular mass and it is having a greater polarity. So due to these two reasons, they are having stronger intermolecular force of attraction. Okay, and if the intermolecular force of attraction is much greater, if it is much stronger, what happens to the boiling point? In order to break that bonds in between this, we'll have to give great amount of energy, so that we can say this causes, these three causes high boiling point for this haloalkanes and haloarenes. And as the molecular, we can say, like, we can conclude it like, as the molecular size increases, intermolecular force of attraction increases, and thus boiling point increases. So we can write it like boiling point is directly proportional to the molecular mass. As the molecular mass increases, boiling point too increases. So for same alkyl group R, boiling point decreases in the order Ri. Alkyl iodide greater than alkyl bromide greater than alkyl fluoride greater than alkyl fluoride. Why it is so? We know that fluorine, chlorine, bromine, iodine are what? Halogens. As we move from top to bottom in a group, what happens? The atomic size increases. If the atomic size increases, molecular mass will be increasing. Now, what about this R? In all these four cases, R or the alkyl group is the same. Okay, so the molecular mass depends only on what? Iodine, bromine, chlorine, fluorine, and among these the smallest one is fluorine, so it will be having small molecular mass, and this iodine will be having greater atomic size, and this one will be having greater molecular mass. As the molecular mass increases, boiling point increases. So this is the order of boiling point. Okay, now for isomeric haloalkanes, boiling point decreases as branching increases. What happens if the branching increases? As the branching increases, surface area decreases, is it? Consider CH3, CH2, CH2, CH2 pair. So it is having 4 carbons, same number of hydrogens, like 2, 5, 7, 9. Okay, so they are C4 H9Br. Okay, so these three are isomeric haloalkanes. Okay, they are having same what chemical formula C4 H9Br, but these are position isomers. The Br is connected to first carbon here, second carbon here, and here is on. Okay, sorry, on second carbon. Here is the other structural or position isomer. Okay, so that they are what isomeric haloalkanes. And here you can see there is no branches, or bromine is the only branch. Here there is, if this is the parent chain, there is one branch. If this is the parent chain, this CH3 and this CH3, there are two branches. As the branches increases, you can see here this has this much of surface area, this one is only this much, this one have only this much. So surface area decreases, and thus boiling point decreases. As the branching increases, surface area decreases, and thus boiling point decreases. You can see here for this one it is 375, it decreased to 364 in this case, it again is decreased to 346 in this case. Okay, now the next is for dihalobenzenes. For dihalobenzenes means on benzene ring there will be two similar halogens. For dihalobenzenes, boiling points are nearly same. They are having nearly same boiling points. Here we have 1,2-dichlorobenzene, 1,3-dichlorobenzene, 1,4-dichlorobenzene. This can be called orthochlorobenzene, metachlorobenzene, parachlorobenzene. Okay, so boiling points are nearly same, but high melting point for the para isomer as compared to the ortho and meta isomers, and this is due to the symmetry of this para isomer. So for isomers, molecular masses will be the same. Okay, for isomers, molecular masses will be the same. So we can say boiling point is inversely proportional to branching. Here we have for every for every hydrocarbons or haloalkanes and haloarenes, as the molecular mass increases, boiling point increases. And for isomers, molecular mass will be the same, since they all have 4 carbons, 9 hydrogens and 1 bromine. They all have same molecular mass. And now we have to look into the number of branches. As the branches increases, boiling point decreases. Okay, the next is density. So bromine, iodine and polychloroderivatives of hydrocarbons are heavier than water. It is because bromine, iodine, polychloroderivatives, so that contains bromine, iodine or chlorine. Okay, more number of chlorines, so it will have a greater molecular mass. As the molecular mass increases, it will become heavier. It will become heavier than water. If compared to water, it will become heavier, since it is having bromine, iodine and the chlorine atoms. So the density increases with the increase in number of carbon atoms, halogen atoms and atomic mass of halogen atom. Okay, so there are 3 cases by which the density increases. The first one is as the number of carbon atom increases, density increases. The second one is as the number of halogen atoms increases, density increases. And the third one is as the atomic mass of halogen atom. So if it is fluorine, chlorine, bromine, iodine, the greater atomic mass will be for iodine, and then for bromine, then for chlorine, then for fluorine. So as the atomic mass of halogen increases, density increases. Here are some examples. The first one is C3H7Cl. Okay, so it have 0.89 gram per ml density. In this case, C3H7Br, that is 1.335 gram per ml. The third one is C3H7I, and it is having 1.747 gram per ml. Here you can see there is an increase in density, and if you consider these halogens, C3H7 are common in all these, but these halogens, chlorine, bromine, iodine. So iodine will have greater atomic mass. So as greater is the atomic mass of the halogen, density will be greater. Okay, so the atomic mass of halogen increases from chlorine to iodine, and that is why the density increased here. In this case, here we have CH2Cl2, CHCl3, CCl4, and if you consider the value of density, for CH2Cl2 it is 1.336, for CHCl3 it is 1.489, for CCl4 it is 1.595. Okay, so Here you can see here 2 chlorines, 3 chlorines, 4 chlorines. As the number of chlorine atoms or the halogen atoms increases, what happens? Density increases. Here from 2 to 4, here the number of chlorine atoms increased from 2 to 4 and thus the density increased. That is about the density. The last one is solubility. So these haloalkanes and haloarenes are slightly soluble in water. Actually, water is polar and also this haloalkanes are polar. And then why these are slightly soluble in water? Here you can see RCl, RCA. So these are two haloalkane molecules. Okay, so they are connected by weak dipole-dipole interaction. In order to break this, what does this soluble in water means? This bond should be broken and this RCl molecule should bond with the one molecule of water. That is called, then we can say the RCl is soluble in water, is it? So first of all, we have to break this bond. In order to break this weak dipole-dipole interaction, we will have to provide some sort of energy, okay, some amount of energy. And here there will be water molecules connected by hydrogen bonding, and you know that hydrogen bonds are very strong. So in order to break this bond in between two water molecules, which is hydrogen bonding, we will have to provide a greater amount of energy. Okay, and now you can say like energy is required to dissolve haloalkanes in water. In order to overcome the attraction between haloalkane molecules and hydrogen bonding in water molecules, we have to provide energy, is it? And now when this RCl, if they are broken by giving or by providing energy, this RCl will bond with the water molecule and it will be, the new bond formed will be dipole-dipole force of interaction, which is weak force. Okay, and during this bond formation, some amount of energy will be released. During bond breaking, energy should be given. During bond formation, energy will be released. So here you can see, here we have to provide small amount of energy, large amount of energy. So we have to provide in total a large amount of energy, but the energy released during this reaction is only a few, because it is a weak dipole-dipole force of attraction. Okay, so this is not favored because only a small amount of energy is released during this bond formation, but in order to break these bonds, in order to break these two bonds, we have to provide a greater amount of energy. So this is not favored, energetically not favored. Okay, but and also due to this energy, why alkyl halides are or haloalkanes are slightly polar in water, even though they are polar. Okay, now they are soluble, these haloalkanes are soluble in organic solvents, and this is due to the new interaction formed in between organic solvent and this alkyl halide or haloalkane having similar strength as those being broken. Okay, so that will be stronger if this haloalkane is bonding with the organic solvent. The bond formed will be much stronger and a greater amount of energy will be released. Okay, and that will be almost equal to the energy required to break this dipole-dipole interaction in between the haloalkanes and the hydrogen bonding in between the water molecules. So this much is about the physical properties of haloalkanes and haloarenes. Okay, the first one was color, then smell, then this physical state, polarity, boiling point, melting point, density, then solubility. This much is about the physical properties.